Welcome to Algebraic Graph Theory Seminar, everyone. Today, our speaker today is Chris Godsil, who is well known to all of us. What was he doing some long time ago, before some of us are even born? So today we have an opportunity to follow Chris to see some of his work with Brendan McKay on cospectral graphs. Chris.
Great, thanks, Sharon. Prehistory is a technical term in this context. It happened some years ago when I pointed a graduate student a paper and they looked at me with shock and said this was written before they were born. And so now we have this concept of prehistoric papers, which was before the grad student or postdoc was born. So it's a technical term. So I'm going to talk about some work that Brendan McKay and I did many years ago on constructing cospectral graphs. So at the time we were both graduate students, and so most of what I'm saying is joint work with Brendan McKay. So now, since I've mentioned history, I looked around a little bit about the history of spectral graph theory, and I found this rather amazing statement. The spectral graph theory started in the 80s. Now, that's a rather strange statement because in 1980, the book Spectral Graphs by Svetkovich, Dubin, and Sachs was published, and there's 368 pages there. And if the first statement is correct, one wonders what they found to write about. In fact, it's worse than that. The paper is often cited as the first paper is by Kollatz and Sinogovich, called Spectrum of Finite Graphs. And it was published in 1957. But Sinogovich died during the Second World War, so it was certainly earlier than pre-1940. Now, also the theoretical chemists were working on what's now called Hückel molecular orbital theory, and they were certainly publishing right up in 1947, 1948. So the spectra of graphs does go back a way, and it wouldn't be unreasonable to take the Kollatz and Sinogovich paper as being the starting point, but the history is always complicated and it's always messy. So that's just by way of background, but I was just annoyed by that first quote. I get to say something about it. Okay, so one thought about cospectral graphs. Okay, so the observation, and I can remember this in my course in graph theory, that the adjacency matrices of isomorphic graphs are permutation equivalent. And since permutations are orthogonal, permutation matrices invertible, this implies the adjacency matrices are similar. And the question is the converse true? Okay. Now, actually, I very recently came across a paper by Reed and Harari and a couple of other people whose names I forget right now. And they stated in there that during a lecture, one of them conjectured that the characteristic polynomial determined the graph. And Bose was in the audience and he gave them some counterexamples very quickly. In fact, it's a pretty silly, it'd be very nice if we characteristic polynomial determined the isomorphism class, because then we could determine isomorphic graphs in polynomial time, but it doesn't work that way. And in fact, now I didn't write down, but since I noticed Willem was there, I should say Willem Hamers has conjectured that the proportion of graphs on n vertices that are not determined by the characteristic polynomial goes to zero as n goes to infinity, but I'll let him talk about that. The reason that this conjecture is a little bit silly is you don't have to try very hard. You can get here are two graphs on 5 vertices, okay, and they both characteristic polynomial t cubed times t squared minus 4. And it's not, you can work these out by hand. So if you're worried about this conjecture or this question, then you can start working out the spectra of characteristic polynomials of small graphs. And you can certainly get to 5 by hand without any particular problems. So we know that the conjecture then is false. Now, of course, this is just one pair of counterexamples. The thing to notice, though, is that the first graph here is K14, and the second graph here is K22 with an isolated vertex. Now, if you add an isolated vertex to a graph, you just change you increase multiplicity of 0 by 1. Okay, so we can deal with isolated vertices very easily, and we'll often throw them away. But anyway, these two graphs are cospectral, and I'll sometimes say that if I delete that middle vertex, that the K14 and the 4 cycle are cospectral, but for zeros. Okay, now So Brendan and I were, for some reason, but very often we both got very interested in this question. And so we thought about some more. Now, one comment is that since they're complete bipartite graphs, you can work out the characteristic polynomial of the complete bipartite graph, KAB. And it's really very easy. It's t squared minus AB times some power of t. Now, this we can fudge with isolated vertices. So we can say that if you ignoring zeros, the spectrum of KAB is determined by the product AB. And so here we have 1, 4 and 2, 2. The product is 4. Okay. And so you then get infinite families of cospectral graphs all coming from complete bipartite graphs. Now, it's not hard to work out the eigenvalues of the complete bipartite graphs. So long as you remember the rule is if you're trying to work out the eigenvalues of the matrix, the best way to do it is to guess the eigenvectors. Now, I do remember an exam we gave some in the linear algebra course once where we gave the students a matrix and a vector and asked them to work out the eigenvalue. And a good fraction of students then proceeded to work out the characteristic polynomial first. But if you've got the eigenvector, you can work out the eigenvalue. Now, the eigenvectors for a complete bipartite graph, you can break up into two classes. There are the ones which are constant on the color classes. In fact, there are two of those, and their eigenvalues turn out to be plus or minus the square root of AB. And then there's the eigenvectors that sum to 0 on each color class. And you can check that any vector non-zero that sums to 0 on each color class is an eigenvector with eigenvalue 0. So you can work this out. You can also do it by determinants. It's not too bad. So so this answers the question. Okay, the characteristic polynomial doesn't determine the isomorphism class of the graph. Now, on the other hand, you might say these examples aren't particularly interesting. You know, we're not really looking for algorithms to distinguish complete bipartite graphs. So why would we bother? Now, this was the observation that we made at the time was that there's another way of looking at this pair of graphs. So I'm going to consider the direct product x cross y. Now this has got infinitely many names: a direct product, tensor product, Kronecker product. But so is the direct product of cosmic graphs. So the adjacency matrix of the direct product is just the Kronecker product of the adjacency matrices. Fine, so that's the direct product. And for some reason in this, I don't know where we got to the product from, but if you look at the direct product of P3 with itself, so we've got you've got vertices. Let me put them in actually, number them a bit. You've got vertices, I'll say 0, 1, 2. Now, so this vertex, so the 9 vertices here are just the ordered pairs of vertices of x and y. And you can check very quickly that this is the direct product of x and y. Now, okay, I've colored in such a way you can see that there's a pair of graphs there, and that's exactly the pair of graphs we were dealing with already. Okay, so that pair, and so this graph this direct product has 2 components. One component is K14, the other is the 4 cycle. Okay. Now, the interesting thing is you can prove if you take the direct product of 2 connected bipartite graphs, that product has exactly 2 components. And you can prove that those 2 components are cospectral, possibly accepting zeros. Okay, so there's a general result about direct products, which implies that this pair of graphs, the pair of graphs I started with, are cospectral. Okay, but it's going to give us many examples. Now, I'll run through a bit of a proof in a minute. The thing to bear in mind is, generally speaking, it's not so hard to find the constructions of pairs of cospectral graphs, but then sooner or later, some unpleasant soul comes to you and says, how do you know these are not isomorphic? Now, that's embarrassing because I don't, as a rule. Now, you can usually, you can certainly always verify it on a computer. You start plugging in examples random, you find that they're not isomorphic. And so you can convince yourself in that sense, and you can, if you work harder, you can probably find an infinite family of pairs and not isomorphic and cospectral. It's difficult to prove that everything you produce will be non-isomorphic, and it's probably not true. Okay, so but as I said, the point is that you can, the rule of thumb is if you come up with a construction, most of the time the things that produces will be non-isomorphic. Okay. Now, okay, so let's think about proving this. Now we're taking bipartite graphs. Okay, so I've got two bipartite graphs here, and I can write the adjacency matrices in this form. So I've got a matrix B and a 0 matrix B and a 0 1 matrix C, and I'm taking the canonical product, and I get this. And when I do that, I get this 4x4 matrix, which I can rearrange to give me this 4x4 matrix, this permutation equivalent to this. So the point about this is the adjacency matrix graph. Each of these things is a 0, 1 matrix. Okay, there's a metric transpose of B transpose tends to C is B tends to C transpose. So this graph has got two components. Okay, one with this adjacency matrix, one without this adjacency matrix. Okay, now they're bipartite graphs. Now for bipartite graphs, the spectrum is symmetric about the origin. And so if you know the squares of the eigenvalues of the bipartite graph, you can recover the eigenvalues. And it's often easier to get the squares. If you look at the squares of this matrix, which I'm here calling M, we get this. And if you look at the square of N, we get this. Now, the problem is that we've got a C transpose there and a C transpose C there. Okay. But there's a theorem, I've got it here. No, I didn't write it in here. So the theorem, well, one thing I want is that if as such that and S are both defined, then RS and SR have the same non-zero eigenvalues. With the same velocities. So, and so that implies, well, C transpose. Well, I'll say a cospectral, but for zeros. Right. So, and so that means that this similar to this, and so we conclude that M squared and N squared are cospectral, ignoring zeros, and so therefore, since they're bipartite graphs, are cospectral. So this gives you a proof. Probably the important thing about the proof is this identity here. We'll be using it again. And I think you can probably argue that most of the examples we have of cospectral things are following from this. I mean, the simple idea is if you have two matrices R and S, and such that RS and SR are both 0, 1, then you've got yourself a pair of cospectral directed graphs. Okay, and so it's a powerful tool. We'll be using it. Okay, so we've generalized. We started with our K14 cycle, and we had one generalization doing this complete bipartite graphs. But we have what, in some sense, is a more interesting generalization in terms of the components of a direct product, a graph with of two connected bipartite graphs. So that gives us, again, infinite families of cospectral graphs. And now the only problem is these aren't earthly connected. And at some point, someone's going to say to you, well, let's just deal with connected. We can always deal with the components of connected graphs. So we should just be worried about whether we can get connected cospectral graphs. Okay, and we don't have any examples just yet. So Well, I'm going to give a construction. This won't make a whole lot of sense to you if you think about it. The idea is I'm going to have two matrices, two partition matrices, L and H, and maybe 3 H prime, which is just H prime is permutation equivalent to H. And the understanding is that these diagonal blocks are square, okay? And we define the partition tensor product. Let me make that a bit prettier. And so I've got L hat. Its product is just so it's kind of a cross between the tensor product and the Sher product, except instead of but okay, so we have these two matrices. Okay, now the theorem which Brendan and I proved is that if L has got this special form, the diagonal secret identity, then the two matrices or two graphs you get from this construction are cospectral if M is equal to N, or if A and D are cospectral. So this gives you a construction of cospectral graphs. Now, Brendan and I proved this, and the proof is pretty horrible, a generating function argument. Many years later, Knuth came up with a shorter proof using singular value decomposition. Now, we were just innocent graduate students at the time. We probably hadn't had a course in numerical analysis yet, so we didn't know much about singular values, but there's a reasonably short proof using singular values. Now, well, this still looks a bit technical, so let's go to the examples. So the first example, got the values for L, H, and H prime there, and A and B. And if you apply that to the graphs you get are the two graphs shown here. Oops. Now, the interesting thing is this is the smallest pair of connected cospectral graphs, okay? And it's on 6 vertices, so it could be found by hand if need be, okay? Now, okay, so we can get the smallest pair of cospectral graphs from that construction. Now, we can do a lot more. I'm not going into all the details, but these two graphs arise from that construction. This is K14 with an isolated vertex, and this is the 4 cycle with 2 isolated vertices. And from this construction, we discover these things cospectral. So the first example I showed you is a special case of this. This is a slightly more complicated example. This gives you a pair of trees on 9 vertices. Now, the way to think about this is that, well, okay, no. We have this piece of the graph, and we're going to just reflect about this line. Okay, and so you can, in a sense, you obtain this from that by a reflection. So if I throw that away and then reflect about this edge, about this line, I get this graph. And the same argument applies in these cases. Now, there's a more general, the constructions are more general than that, but this is good enough for us. And so you can see here that we've got 3 pieces. This is path on 3 vertices, path on 3 vertices, path on 3 vertices. And so these two graphs are going to be cospectral. They're cospectral trees on 9 vertices. Now, the smallest trees, the cospectral, are on 8 vertices, and they were found by Collatz and Sinorovitz. I'll come back to that. You can do other things. Here, these two graphs are cospectral, and these two graphs are cospectral. Now, this is just a cycle of even length. And so the conclusion then is that, or one conclusion, the spectral radius of this graph is 2. This is regular, and they're just zeros. So the spectral radius of this is 2. Okay, now this is the path on 3 vertices. You're talking about it is 0 plus or minus root 2. So the spectral radius of this is 2. And so from this, you get a proof that the spectral radius of the, or 2 copies of P3 joined by a path is 2. And the last one here is another construction giving you the smallest cospectral forest. Now, Brendan and I we did a lot of computation and looking at small graphs. The problem with getting the character at the time, we're trying to get the characteristic polynomial, and we didn't have the numerical analysis libraries weren't what they are now. So we were using some code which computed the zeros of polynomials. And the problem was that if there was a bit of rounding error stuff, then the zeros would come out complex but we're dealing with adjacency matrices of graphs. And now the problem is if there's an eigenvalues of large multiplicity, then you're almost certainly going to get some, when you do the numerical computation, you get complex eigenvalues. And so that's a bit of a nuisance. But anyway, it is what it is, and it's easier now. So I won't go any more into that. What's the time? So, okay, so we have this reflection, sort of call this a reflection construction, and it's actually a bit more general. The maybe I'll put a picture in here. The idea is that you pick a graph. Oops, that's not one. Graph Y, and you have them joined up in some fashion, which is probably not symmetric, just to make it. So we get this structure, and we start. So we have this, and we have a bipartite graph. Details don't matter too much. And the rule is that wherever there's an edge, you put a copy of X here, copy of Y there, and you join them according to that rule. Okay, and so now you get a graph. Okay, and then that, and now there's two ways you can do that. Of course, I put X here and Y there. I could be choose to be difficult to put Y here and X there, so I get two graphs. And those two graphs will be cospectral if the number of white vertices equal to black vertices, or if the graphs X and Y are cospectral. And so that construction gives you all the examples I showed before. But for the first case, it's just a simple reflection. So that in that case, with the reflection, our bipartite graph is just the K12. Okay, so if we use that, we get the reflections examples I've been showing you. We can get more examples by doing that. And as I said, the proof of this is a fairly horrible generating function argument. And Knuth then showed how to do that with using singular buggy decompositions. Okay, so we now have a construction for connected cospectral graphs. Okay, so that's nice. The issue then is that when we're doing our computations, we discovered there's a strong tendency for cospectral graphs to have cospectral complements. Okay, and so it's a very strong tendency. I don't have any numbers here to show you, but so if you're picking up pairs of cospectral graphs, they are often going to have cospectral complements. And so we were thinking about that. Now, actually we started from something a little different. We started from subdivision graphs. So subdivision graph, and you take a graph and you put a new vertex in the middle of each edge. Okay, so now you've got if the graph's got V vertices in the edges, the new graph has got V plus E vertices, E of which have valency 2, and the new graph is subdivision graph is bipartite. Okay, so if it's bipartite, the adjacency matrix is in a zero matrix transpose 0. Okay, so what's the matrix? So the matrix is what I call the vertex edge instance matrix of X. So the rows are indexed by the vertices, the columns by the edges, and there's a 1 in the ij position if the ith vertex is in the jth edge. Now, okay, so that's a well-defined matrix, and it's got various uses. One thing you can see is that BB transpose is equal to the degrees plus the adjacency matrix. This is sometimes called the ensemble passing. On the other hand, B transpose B is 2i plus some 0, 1 matrix, which turns out to be the adjacency matrix line graph. Okay. Now, from that rule I was quoting before, it follows that these two matrices have the same non-zero eigenvalues and the same multiplicities. Okay, so that implies that since this is positive semi-definite, this is positive semi-definite, and so any eigenvalue of a line graph is at least -2. But that's not going to bother us today. Now, for the subdivision graph, you can then verify that the adjacency matrix subdivision graph is just this guy. Okay, so we have a formula for the adjacency matrix of the, I don't know why I wrote line graph there. Okay, so and since it's by part, the argument is symmetric, and so we can take the square and then work with that. And so if we square S, then we get BB transpose B transpose B. And so that's got two blocks. One is the unsigned class, and the other is a line graph with plus 2i. So we get that matrix. So the eigenvalue is a subdivision graph, and determined by the eigenvalue is the line graph. And conversely. Okay. Now, and so this is, well, the same statement I made before, but I repeat it, this is important. So I want to pick a particular pair of examples. Well, I can draw it here. The examples I want to consider are these two graphs. Now, these two graphs, the special property of these two graphs is that they have the same line graph. And so the point is that from the graph, you can't always construct a line graph, and the source of the problems is exactly this pair of graphs. Now, since they have the same line graph, their subdivision graphs are going to be cospectral, but for zeros. Okay, so let's actually work this out. And so, okay, so you work out the two vertex edge instant matrices for the triangle and or for K13 and the triangle. And you discover that, okay, here we have the adjacency matrices for the subdivision graphs of those two things. Subdivision graph of the K13, of course, is this guy. And the subdivision graph of the triangle is just a 6 cycle, but I've thrown in isolated vertices to make number of vertices equal in two cases. Okay, so one consequence of this is that these two graphs are cospectral. Okay, now it would be easy enough to work out the spectrum of these things directly, but the point is that in this case, it actually follows from something, also, you know, something a little strange. And the other thing is that their complements are cospectral. Now, I was sitting there staring at these things, and so I'm thinking I can compute eigenvalues of, you know, cycles and trees by hand without too much grief. But the complements, well, they're going to have lots of edges. I don't want to deal with the complements. But I need to show that the complements are cospectral. Now, up to this point, you know, what tools have in mind? We have some walk generating function arguments, and we have, you know, determined type things, characters polynomials. But neither of these look like being too useful. And so the thought occurred that, well, if I want to show that S1 and S2 are cospectral, it would be enough to find matrix L such that L inverse S1, L2. You know, so I'm being late. So if I can find the change of basis, if you like, that takes S1 to S2, then I've got to prove they're cospectral. Okay. Now it turns out we can do that in this case because the way of lining things up that this matrix here plus this add to the all ones matrix. So if you like, this is the complement of things there. Okay. And so, well, the trick to notice is that if I take this matrix, half of J4 minus A4. Now, J4 has got eigenvalues 4 and 0. Actually, I got the commas, the parentheses in the wrong place. So J4's got eigenvalues 4 and 0. So half of J4's got eigenvalues 2 and 0, and half of J4 minus I4 has got eigenvalues 1 and minus 1. Okay. So that tells me in particular that the square of this matrix half J4 minus I4 is equal to identity. So this is orthogonal. Yeah, that's right. And you can check very quickly that it maps the columns of this guy to the columns of this. And so this leads to a construction. So assuming I've got a Cartesian matrix shown as here with diagonal block square, and I'm assuming that C is regular. Okay. And I'm going to assume that B is L by M with L even, and that each column B is 0, 1, or is exactly half bent equal to 1. So you can see here that this has the half property and this has the half property. Okay. So define Q to be 2 and LJL minus IL. And Q symmetric and Q squared, that's a squared. Q squared is the identity, so it's orthogonal. And when you do the calculations, you're applying QI fore and aft. You get this. Now, C is regular, so QCQ is just C. And QB is going to be a 0, 1 matrix, and BT and its transpose is 2. So this is the AGT matrix of a graph. And this is a AGT matrix graph, and those two graphs are cospectral. Also, because you check that QI is equal to I, it follows that the this matrix commutes with your ones matrix, and so we get that the complements are cospectral. Okay, and so I didn't need any determinants, I didn't need any generating functions, I just needed a simple calculation with these guys, using the fact that I could so I use this matrix, okay, and so I get the change of basis explicitly, and so then we get this cospectral pair of cospectral graphs, cospectral with cospectral complements, and this is the well, it's a slightly simplified case of what I call local switching, okay, and so there's a messier and somewhat more general construction. One thing about this is that if you look at the graphs up to about 9 vertices or 10 vertices, most of the examples of graphs that are cospectral arise from the local switching construction. So it's quite powerful. Now, you can also convince yourself by a probabilistic argument, which I never wrote down, that the number of graphs which will emit a local switching is going to go to, or proportion of graphs that emit a local switching is going to go to 0 as the size of the graph goes to infinity. So it's not going to, so it doesn't, it's not going to give you a CAN example to Willem's conjecture. Okay. But what happens is that the behavior on the small examples, up to 9 or 10, is not typical of a long-term behavior. And that, unfortunately, is pretty much a rule of thumb when you're dealing with spectral things, is that the small examples can be quite misleading. So, I've given you 3 constructions. We've given you the direct product construction, or what we call the partition tensor product, and the local switching. Okay, and the point is, in each case, we were starting with these small examples and just trying to generalize them. And it's surprising how often that if you come up with a construction of a pair of cospectral graphs, you can find a generalization. I want to go on to talk a bit about trees, because certainly one of the starting points. So I mentioned that Kolatz and Sinorovich in their paper had Kolatz in the paper had a pair of trees and 8 vertices that were cospectral, nice, small, big, and that's the smallest pair of trees. Now big theorem about trees is due to Schwenk, who proved that the proportion of trees on n vertices that are determined by their spectrum goes to zero as n goes to infinity. So this is the opposite of the will infinity active for trees. The spectrum is not a useful invariant in distinguishing trees. Okay. Now, how did Schwenk do this? Well, he constructed a graph with two special vertices, a graph on 9 vertices. And he told me once how he did this. He had a deck of cards with each of the trees up to at least up to 9 vertices drawn on it. And he was standing in line waiting to get tickets for a football game or something. It's a silly idea, but there he did. And so while he was doing that, he was amusing himself by computing the character files of trees with vertices deleted. And so he came upon, well, this is the same tree twice. And the key point here is that if I call this tree S, then S with vertex 4 deleted and S with vertex 7 deleted are cospectral. Now let me add a page. So we've got these two limbs. Now, the idea is that if I take, let's just draw a 4 here, a mess, 7 here, and I come along with some other graph with a chosen vertex, call it U, and put it here. So we have X. So we're using the same vertex in X in both cases. So I'll put an A there and an A there to indicate that. So here I'm merging vertex A of X with vertex 4 of Schwenk's first graph and with vertex 7 of the second. Now, there's a couple of ways of proving that the characteristic polynomial of if I have two, if I have two graphs X and Y and I pick a vertex A and X and B and Y and merge them, then I get X drop A. I'm going to leave out the T's. So this could be proved in more than one way. Schwenk proves it using just by expanding determinants, which is probably not which works pretty well if you've got a blackboard to do it. So the point about this identity is it tells you the spectrum of this is determined by the spectrum of X, the spectrum of Y, and the spectra of X drop A and Y drop B. Now, the point about in this case, this is Y. Okay, let's put it in color. So let's call this Y now. And so the point is that Y drop 4 and Y drop B are cospectral. And so it follows that these two graphs are cospectral. And so once you have a tree like the one that Schwenk found, you get infinitely many pairs of cospectral trees. It's fairly easy to show in general these non-isomorphic. Okay. Now, so that's step one. I think this idea, certainly I learned this identity from Schwenk. That probably wasn't any earlier. The second thing that Schwenk did was to prove that the proportion of trees on n vertices that contains this stuff. We say that this here is a limb of the big tree. This is a limb, okay. And the proportion of trees which have Y rooted at 4 as a limb on n vertices is equal to the proportion of trees that have Y rooted at 7 as a limb. In fact, the proportion of trees that have a given limb is only determined by the number of vertices in the limb. And so from that, by a power series argument, you can deduce the proportion of trees on n vertices that are determined by the spectrum goes to 0 as n goes to infinity. Now, this last part is a bit technical and it was proved in Schwenk's thesis, but Schwenk says it's very complicated, never published it. There was a shorter proof found by Kevin McAvaney using standard polyar arguments later on. So it's a nice result with a reasonably well contained proof. Now, okay, so almost all trees are cospectral, have a cospectral mate, but I've been going on about how most graphs, if they're cospectral, they tend to have the cospectral complements. Can we do something for trees? Well, Brendan and I were doing our searches and we came up with this tree with vertices 4 and 8. And again, we discovered that, well, if I call it S drop 4 and S drop 8 are cospectral. Now the complements are cospectral. Now, for saying they're cospectral, well, in this case, it's both these claims are easy to see because S drop 4 and S drop 8 are actually isomorphic. You bleed 8, you get here you get a path of length 3. If you leave 4, you get a path of length 3, and this long tree with double tail at the end, double start at the end. But lead 8 here, I get the same graph. So the actually, I only noticed this last night. Brent and I never observed it, but the point is these two trees, these two vertices have the property that S drop 4 and S drop 8 are isomorphic, so they're cospectral and their complements are cospectral. Okay, now having cospectral complements might be useful, but it doesn't prove anything. The argument I was sketching before tells me that if I have a tree with this as a limb and replace it by this, the replacement is cospectral. But I need cospectral complements. And all I'm going to say is that there is an argument. It's not as bad as the proof of the generalized tensor product argument, but there's an argument which tells you that if we, by replacing this limb by this limb, the spectrum of the complement's preserved. And so we have a limb on 11 vertices. And so now we've proved that almost all trees, for almost all trees, there's a second tree which is cospectral with cospectral complements to it. Okay, and so that generalizes Schwenk's result. And actually I'll leave that there. This is I won't go through the proof. I want to go on to something else. Yeah, let's go skip this. Two things I want to do. First thing is, okay, so we produced that found a tree with a pair of pseudo-similar vertices, although I didn't realize at the time. Now, in fact, the construction of graphs with pairs of pseudo-similar vertices goes back to a work by two chemists, Herndon and Elsie. Okay. And what I've got here is an example of the construction. So I'm going to get it from this. I've got a graph here on 12 vertices. I'm going to get a tree on 11 vertices with a pair of pseudo-similar vertices. And it's just occurring to me as I talk, this may well be the same pair of trees that I have before. It may well be the same pair of trees I had before, but let's go on with that. So this is our graph. Okay, we've got a 9 cycle and we've put vertices degree 1 on like that. So there's an automorphism aboard a 3 rotating it. And there's also a reflection. So the automorphism group of this graph will have order 6 at least, probably just 6. Now, what we're going to do, well, so now we do have this automorphism order 3. And so the vertices 1, 4, and 7 are equivalent under the rotation by, so you make 1 to 4, 4 to 7, and 7 to 1, and shift everything else accordingly. But what I'm going to do, if I do it in the drawing, what I'm going to do is just cut out this vertex. Now I have a tree, and my claim is that that tree that I get by leaving 1, the vertices 4 and 7 are pseudo-similar. Okay, now, so this is a nice construction. It's easily generalized. I'll show you one more example in a minute. And you can prove, in fact, that if you have a pair of pseudo-similar, a graph with a pair of pseudo-similar vertices, then you can, in fact, always construct the graph using this construction. There might be other ways of doing it, but you can always use this construction. Okay, and I proved that. Fine. Now, just to show that you can do more with it, this is the simplest example. If I take a 6 cycle and put the triangles as shown, then the vertices 2 and 4 are pseudo-similar in this. So there you have a graph. So 2 and 4 are pseudo-similar. Okay. So the point is, this is a general construction, and it's due to 2 chemists. And I should say that the chemists were working on graph spectral stuff, certainly publishing stuff in 1947 and things like this. So Hendon Elsie was more recent. Now the final graph I want to talk about is the yet another tree that Brendan found. Okay. Now what happened was that Von Mullen asked whether the distance, the spectrum, whether trees could be characterized by the characteristic polynomial of their distance matrix. So this is the matrix with entries indexed by vertices, and the UV entry is the distance between the vertices U and V. So it's the distance matrix. And Ron Mullen actually conjectured that the distance, the characteristic polynomial of this matrix would be an invariant for trees. Now, Brendan proved this was just, well, in a sense, this was spectacularly wrong. So he came up with this tree on 16 vertices, with these 2 vertices. And again, these 2 vertices are cospectral. Their complements are also cospectral. Okay. And what Brendan showed was that if I go back to my colors again, we could glue something on here or something on here, so we get 2 graphs, depending which one we choose to do. Those 2 graphs had the same characteristic polynomial, their complements had the same characteristic polynomial, they had the same Laplacian. The spectrum, their distance matrices were the same. The spectrum of the normalized Laplacian was the same, although that was proved by later by someone else. But so this tree, using this tree, you can produce a counterexample to almost any polynomial you're going to try and write down. And so, okay, and I just wanted to, well, I just listed some papers. These are the things that Brendan and I wrote back ago. Knuth wrote a book paper called same title as ours, Partition Tensor Products and Their Spectrum, in 1995. Herndon and Elsie paper was published in 1975. The part of Schwenk's proof that he was in his thesis and he didn't present is now given in 3 pages. There's a 3-page proof by 3-page proof by Kevin McAvaney. So that was the, and that also sort of gives you some idea of the timeline. I don't think I want to. And I'm afraid you get no rear ends of animals today. That's all I have to say.
Thank you for the nice talk, Chris. Any questions? So the construction using direct product so bipartite graphs, it works for all connected bipartite graphs?
Yeah, I don't think they need to be connected. It's just a bit easier. You get yourself confused. You have to start worrying about which component, deciding you get a graph with many components, you have to divide the components into 2 groups. But it does work for any. And so some of the time the graphs will be isomorphic, of course. So I think of P4 times P4, I think that one, but it's easy to find examples without isomorphic.
Did you see the for n bigger than equal to 10 or 11, most of the cospectral graphs are obtained from local switching?
Yes.
I didn't know that.
Well, it's a good proportion. So that, and so this is one. I mean, the point is, if you look at the data for graphs up to say 10 vertices, then you would think that Willem must have been in an unusual state of mind when he made the conjecture, because the proportions seem to be going up. But what you're seeing is the effect of local switching. And if you eliminate that, then you realize that, okay, it seems much more reasonable that most graphs should be determined by the characteristic polynomial. And again, this is all related to the fact that the small examples give you the wrong idea. And there's also a parity effect, which I have no explanation for, in the sense that behavior on the even integers is a bit different from behavior on the odd integers. So there's an even odd effect.